In this lesson, we'll be talking about optimization problems. Optimization problems are actually one of the most useful types of problems in the real world and one of the main applications of a derivative. The idea of an optimization problem is to find the maximum or minimum value of a function. And you can imagine how useful this is in the real world. To give a few examples, in mathematics or especially computer science, you want to minimize your error. Finding a minimum error could be used with statistics, could be used possibly with an algorithm that you're using with your computer. Numerical analysis does a few things like this. In biology, you might be considering something like you're designing a new drug and you want to figure out what is the proper dose to maximize the benefit. You might be able to create a function that tells you how well it's doing its job and find the dosage that does the job best. In business, these are a big thing. Wouldn't you want to maximize your profit or perhaps minimize your costs? All of these are great examples of the types of ways that you can be more efficient by using a derivative to find a max or a min. Let's start with a simple introductory example to motivate this. You've got a rectangle with a perimeter of 40 feet. How can we maximize the area of the rectangle? How could we rearrange the sides of the rectangle? But what I'm going to do is make a little chart for the length and width that we could do. And I will note here that the perimeter of a rectangle is 2L plus 2W. And we want that perimeter to be 40. So you might even, just to make your life a little easier, note this means that L plus W equals 20. So if we find the length and the width, then we'll find the area. Note that the area is the length times the width. For two numbers adding to 20, we might try something like 2 and 18. Then the area would be 36. Maybe we could try, say, 1 and 19, but then the area would be 19. How about 5 and 15? Then the area is 75. Maybe something like 10 and 10. Then the area is 100. Maybe we could try, say, 9 and 11. Then the area is 99. Maybe to try one more, 8 and 12, I get an area of 96. So just by trying some different dimensions that give the rectangle a perimeter of 40 feet, it looks like 10 by 10 has the biggest area. Let me give you a little bit of a background on what we can do here. What I'm going to do is solve this equation for L, and then I'm going to use these two facts to plug in to my area function as length being 20 minus W times W. Notice what I did there. I took my area function and I used what I had known about the perimeter to write the function in one variable. Well, this turns out to be 20W minus W squared. And look at this. I have a function. I can find its maximum. So I'll take the derivative. The derivative is 20 minus 2W, and I'll set it equal to 0. From this I get W equals 10. And since the length was 20 minus W, I get that the length is 10 also. So what I did was found that when the derivative is 0, which is where we know maximums and minimums could occur, that seems to be the actual maximum area. It's the place where the area is largest, and that turns out to be when the width is 10 and when the length is 10. I haven't really formally given your strategy, but this is the way that tends to work. I will point out one more thing, and that we can use the graph here. Notice that this is a downward opening parabola. So at 10, I do expect there to be a max. Let's try another one, and then we'll do even more with the strategy. So what we have is an identical pen that shares one side, and we have 1,200 feet of fencing material to build this pen. We've got two pens together. What can we do to maximize the area of each pen in this setup? A rather simple example, but you can see that something like this might be a decent idea. If you want to make the largest pen that you possibly can with a certain amount of fencing, do a little optimization. The usual strategy for this is to label one direction as X and the dimension of the other pen, just a single pen, as Y. And so what we have, if we look at it, we've got 3 sides of length X and 4 sides of length Y. Now you could do this a little bit differently if you wanted to and call this whole side y, but that tends to make the problem harder in general. What we're going to do is write down that 3x plus 4y is my fencing, and I get that to be 1200. Here's the usual strategy. First, write a constraint equation. Write down something that tells you this is a quantity that I have a limit on, and I'm going to write an equation that models that. The next step is to solve for one of these. So I'll solve for x in my example. I'll subtract 4y from both sides, and then I'll divide by 3 to get x equals 400 minus 4/3 y. So step 1 was get a constraint equation. Step 2 is solve it for a variable. Step 3 is figure out what you're trying to optimize. So let's look at the question again. We want to maximize the area of each pen. Now they're identical, but the area of one of those pens, and this is why I chose to use the y here, is that the area of each pen is xy. Now substitute in this value for x. It's 400 minus 4/3 y, and we still have y because we're doing x times y. So we get that a equals 400y minus 4/3 y squared. With that said, I have an equation in one variable. Now I want to find the maximum value of that equation. So I'll take the derivative, and I get 400 minus 8/3 y, and I'll set that equal to 0. I get 400 equals 8/3 y, and you guys hopefully know this trick, that to get rid of a fraction you multiply by the reciprocal on both sides. So I get y equals 400 over 8 is 50. 50 times 3 is 150. So I get y equals 150. And then I go back and say, well, what does x have to be? X was 400 minus 4/3 y. So I get 4/3 of 150 is 200. So I get 200. We have a likely maximum. Again, the reason that it's a maximum here is because this area function is a downward opening parabola. But I'm going to give you another justification. I'm going to calculate the second derivative. Second derivative is the derivative of this, so I just get negative 8/3. Negative 8/3 is less than 0 everywhere. So by the second derivative test, we have that this thing is concave down everywhere. That's all we need. Everywhere where it's concave down, by the second derivative test, it is a maximum. And based on the rest of the graph, we can see this is the absolute maximum. So y equals 150 is the absolute maximum. All we should do now is finish answering the question. What dimensions should he use to maximize the area? The pens should be 150 by 200, where 150 is the adjacent side's length. The area is 30,000 feet squared. Here's a formal writing down of what the steps are. First off, draw a picture if you need to. You've got to understand the problem before you can get anywhere. Second, write a constraint equation. In every problem you'll be told you have a limited quantity of something. So what you do is you write a constraint equation for each limitation. In order for this to be a truly good optimization problem, with a single unique solution, you need to have one less constraint equation than the number of variables in your problem. I had length and width in my first example, and I had one equation. For the perimeter, I had x and y for my second example, and I had one equation for the amount of fencing. So that's how we set it up. One less constraint than the number of variables. Then we write an optimizing function. This function represents the quantity you are trying to maximize or minimize. In both of our problems that we've done already, we looked at area as the optimizing function. Then what we do is we write the constraint in terms of one of the variables and substitute it into the optimizing function. Get the optimizing function down to one variable. Then with one variable, we find the critical points, and check whether it's an absolute max or minimum, and usually we'll use the second derivative test for this. Then we'll find the value of all the other variables. We'll just use back substitution, and then we'll write a sentence to answer the original question. Let's find two numbers whose difference is 100 and whose product is a minimum. I'll call my numbers x and y. Remember, the word difference means subtraction. My constraint is that the two numbers have to have a difference of 100. X is equal to y plus 100. That's a constraint. We want to check the product and see which has a minimum product. So the product of the two numbers I'll call p. Well, that's just x times y. So if I plug in x being y plus 100, I see that my product is equal to y squared plus 100y. So if I pick y, I immediately find the whole product without having to even calculate x at all. The next step is take the derivative. P prime equals 2y plus 100, and set that equal to 0. I get 2y equals negative 100, so y equals negative 50. That's interesting. A negative number. You might not have thought of that when you first thought of this question. Find two numbers whose difference is 100 and whose product is a minimum. You might have tried something like 300 and 200, or maybe 100 and 0. 100 and 0 has a difference of 100 and the product is 0. That's pretty small. But this time I think we'll even get a negative product. X equals y plus 100. We get that x equals 50. All we need to do from here is use a second derivative of 2y plus 100 is just 2. And this is going to force us to know that this is the minimum. This is greater than 0. So this is an absolute max by second derivative test. The second derivative test gives you that if it is concave up at the critical value, it's a min. If it's concave down at the critical value, it's a max. This is a max, so let's write our final sentence. The two numbers are 50 and negative 50. This one is an efficiency in the manufacturing process. Suppose you're trying to make a cardboard box. And the way that you're making the cardboard box is you're starting with a square piece of cardboard. It's 3 feet wide, and I did say it was a square. What we're going to do is cut out equal squares and fold the sides up. So I definitely need to draw a picture of this for you guys. So the idea is you start with a piece of cardboard. It's a square piece of cardboard. And what we're going to do is cut off a square from each side and fold up these new flaps. So a fold would be right here that you would fold up. You'd have a fold here that you'd fold up, here that you would fold up, and here that you would fold up. And when you do that, you should get your box looking something like this. This is your open box. Down here is the base of the box, and the top is just an open space with sides coming up to hold things. The square piece of cardboard is 3 feet wide. In this case, let's write that as 36 inches, because that'll come in handy for this problem. How should you cut the size to maximize the volume of this box? We need to figure out what the volume is here. It turns out that we don't have a constraint really, because we only have one variable. But we can write the volume in terms of this variable. If you imagine what's going on here, you'll notice that the height of the box is actually x. Because this quantity, when it's folded up, does give you this x height. The width of the box would be this length, which was 36, but we subtracted x twice from it. So we get 36 minus 2x. And similarly, this one is also 36 minus 2x because we're cutting squares from a square. The volume of the box is length times width times height. Let's just go through and write that out. We get V equals 36 times 36, that's 1296, minus 72x minus 72x plus 4x squared. All that is times x. So I get 1296x minus 144 x squared, and I get a 4x cubed. There's our volume. So if we take the derivative and set it equal to 0, this will get it. We get 1296 minus 288x plus 12x squared. But if you set this equal to 0, you can divide by 12 right off the bat, and you end up with the equation x squared minus 24x plus 108. That's still a little bit hard to factor, but it can be done. All you'd have to do is find the two numbers, but if you can't find them so easily, use the quadratic formula. Anyway, I get x minus 6 and x minus 18. I get x equals 6 or x equals 18 for my two possible critical numbers. I don't know which one's which. Which one is the max and which one is the min? I'll tell you one of them is kind of obvious. Just plug 18 into here and notice what you get. If you plug in 18, 2 times 18 is 36. 36 minus 36 is 0. So at 18, you get 0 for the volume. So that actually turns out that this one is the minimum. So the maximum must happen at 6 inches. Let's go ahead and calculate the second derivative real quick. V double prime would be negative 288 plus 24x. And notice if you plug in 6, you end up getting negative 288 plus 24 times 6. I get negative 144. That's less than 0. So this is a max. Let's take a look at the question. How big should you cut the squares? 6 inches each. Cut 6 inches to maximize the volume, 3,456 inches cubed.